Welcome to the deep dive. Today we're tackling a really pivotal challenge in AI, building these, truly unified models, the kind that can understand and generate across everything we encounter, text, images, speech, all mixed together. It's really about moving past AI that only has one sense, if you will, toward something, well, much more holistic.
Absolutely. I mean, think about our digital world. It's not neatly divided, is it? It's this constant flow of different kinds of information. So for AI to really get it to interact meaningfully, it needs to handle these different modalities, all within one single framework. We've seen hints of this potential, like with models such as Chameleon recently. They show amazing promise for creation, translation across modes.
Right, but as we aim higher for that deeper integration, the complexity just skyrockets, doesn't it? The sheer amount of computation needed to train a model that gets language and visual detail and audio signals simultaneously, it's staggering. It feels like we're really hitting some practical limits.
Exactly that. And that's precisely where the innovation we're diving into today really comes into play. We're going to explore this thing called the mixture of transformers, or moat architecture. It's based on some pretty fascinating research, and this work tackles those computational bottlenecks head on. It suggests a pretty fundamental shift in how we actually design these multimodal models.
Okay, so MOTI, let's unpack this key phrase they use, modality-specific parameter decoupling. What does that actually mean, in practice, and why is it potentially such a big deal? Our mission today is to really lead under the hood of Moat, understand what's truly innovative and what it could mean for building, well, better and more efficient multimodal AR.
Yeah, and to really appreciate what's new about mode, it helps to quickly look back a bit. The sort of initial approach for multimodal was often early fusion, basically just mashing different data types together right at the start at the input layer. You can think of it like throwing all the ingredients for a really complex recipe into the bowl right at the beginning. The hope was it allows for these rich, low-level connections.
So with early fusion, the idea was the model would learn, say, the link between a specific word and the pixels it refers to, like really early in the process.
Precisely. But when we tried to scale those up, we ran into issues, efficiency, specialization, things like that. So later approaches started bringing in more modularity. Some folks experimented with making parts of the model sparse, depending on the input type, using these things called mixture of experts layers. Others took powerful pre-trained language models, LLMs, and then sort of bolted on and fine-tuned extra modules for vision or audio. There were definitely steps towards using parameters more efficiently.
Right. So a growing sense that maybe one giant network trying to learn everything wasn't perhaps the best way for handling such different data types. Okay, so how does Mochi take a more, I guess, radical step away from those earlier ideas? What's the real innovation in this modality-specific parameter decoupling?
Well, the core idea in Mode is to move towards having largely independent transformer networks. You can picture them as separate processing towers. One tower for text, another for images, maybe another for speech. Each tower has its own set of parameters, primarily focused on its specific job processing visual stuff or audio or language. This is quite different from architectures where parameters are, much more shared and tangled up across modalities right from the get-go.
Ah, okay. So instead of one massive tangled network, you have these specialized engines working side by side. I think figure one in the paper shows this quite clearly, these separate blocks for image, speech, text transformers.
Exactly. And a really critical part of this design is that each of these modality-specific transformers can be trained with the loss function that's best suited for that data type. So for instance, the image transformer might use a diffusion-based loss that's really good for generating high-quality images. It learns by reversing noise, basically. Whereas the text transformer would likely use an autoregressive loss, predicting the next word. It just wouldn't train a vision model the same way you train a language model.
That feels very intuitive. Different data, different statistics, different ways they're generated. So, what are the big upsides of doing this decoupling? The paper mentions more stable training, which is, often a huge headache with these deep networks.
That's a key benefit, definitely, especially when you compare it to earlier attempts using mixture of experts or MOE. In MOE models, you've got the expert modules and the router that decides which expert gets the data. Both need training right from the start. And this can get unstable if the router isn't learning well early on. Maybe some experts don't get used enough. Modi kind of sidesteps this. With separate, dedicated towers, each one can focus on building solid representations for its modality from square one. It's like letting students master their subjects before a group project.
Okay, this is where it gets really interesting for me. The paper points out that Modi's efficiency boost isn't mainly from having fewer parameters overall in the main transformer parts. Can you explain that? It sounds a bit backwards. Fewer parameters usually means less compute, right?
Yeah, that's a really crucial distinction they make. In their experiments, they were careful to make sure the total number of parameters in the core transformer layers of moat was pretty much the same as a standard dense single-tower multimodal model. The efficiency win for moat comes from the specialization that decoupling allows. Each parameter inside, say, the image tower is just more effectively doing work relevant to images. This is different from standard MoE models, which often do have a larger total parameter count because they have multiple parallel expert branches.
So an OE might look like it has more raw power just from counting parameters, but Moat gets more efficient because its resources are better focused. It's more about smart allocation than sheer numbers.
Precisely. And the results they show really back this up strongly. The research demonstrates MoColor gets to a lower training loss, and it does it in fewer training steps, not just compared to dent models, but also compared to an OEM model with 4 experts, which they call MoV 4X. If you look at the training loss graphs, the moat line just drops faster consistently.
And they put a number on this with that steps to match dense metric. The ENS value, as they called it, was much lower for Moat than MoE 4X, right? Showing it learned much faster.
Exactly. That's S value basically captures the learning rate. Lowers for moat means way fewer training iterations needed to hit the same performance level as a dense model. And what's more, figure 19 in the paper shows this training step advantage translates into even bigger savings in actual wall clock time. That's huge for practical training of these enormous models.
That's absolutely critical for actually using these things. It's not just theory, it's reducing the real time and cost.
Indeed. And this benefit, better performance, faster, those just for one modality or one size. The paper shows this consistent pattern. Lower validation losses for moat for both image and text tasks. And it held up even as they scaled the models up to different sizes. That's all in their validation results. And appendix figure 24, I think. It really suggests there's a fundamental architectural advantage here.
Okay, now they also dug into multi-objective training, specifically generating text using that standard autoregressive next word prediction method, and also generating images using a diffusion approach, learning to build images by reversing noise. Why is training for both at once important, and how did Moat help there?
Right. So multi-objective training is really essential if you want versatile AI that can juggle different tasks and modalities at the same time. For these tests, they use the Llama 2 text data and tokenizer for language. And for images, they used a compressed format VAE encoded latent patches from Shutterstock Images. You can think of these patches as a sort of abstract, efficient summary of the visual information, much smaller than raw pixels. They even use special markers like BOI for beginning of image and EOI for end of image to signal where image data started and stopped in the input stream.
So they were essentially feeding the model this mixed stream of text tokens and these compressed image bits.
Pretty much, yeah. And one of the key findings was that Moten made this combined training significantly more efficient. Figures 10b and 10c in the paper show that when using diffusion for images, the image training loss went down much faster with Moten compared to the other architectures. And that matters because, as they point out, validation loss in diffusion models is actually a pretty good predictor of the final image quality, how good the generated images look to humans.
So it sounds like Mook's separate design lets it optimize the learning for each goal, language modeling and image generation more effectively, maybe without them interfering with each other as much.
That's a really good way to put it, yeah. And allows for more independent optimization. Now let's talk scalability. The paper really stresses that Moat consistently performed better on image generation tasks across different sizes, 163 million, 760 million, up to 1.4 billion parameters. They measured this using standard scores like FID and SLEEP. FID tells you about realism and diversity of generated images compared to real ones. That measures how well images match text descriptions. Figure 12 lays out these improvements pretty clearly.
So Moat isn't just faster to train, it's actually producing better results, especially in that really tough domain of image generation.
Exactly. Now for text-only tasks, Moat was generally on par with the dense models, similar trading and validation loss. But it showed an edge in cross-modal tasks like image captioning, getting higher CIDR scores. CIDR measures how well a generated caption matches the meaning of an image. This kind of hints that maybe the dedicated image training in Moat leads to a richer visual understanding, which then helps generate better descriptions in language.
That's interesting. Though the paper did note Moat showed less improvement for pure text generation at their biggest scale, around 7 billion parameters. Any thoughts on why it might plateau there?
They offered a couple of potential reasons. One is simply that text generation particularly with these huge language models, might already be a pretty efficient process to learn. So the benefits of strict modality separation might just be less dramatic compared to image generation, which is inherently more computationally demanding. They also suggested that maybe getting further text gains at that scale might need different kinds of sparsity or maybe other architectural tweaks beyond just the basic mode setup.
Let's dig into those ablation studies in Figure 14. Those experiments where they selectively untied, made modality-specific different bits of the transformer are always so revealing. What did they find about which parts benefit most from specialization?
Yeah, those ablations were really key to figuring out why Moti works so well. The biggest takeaway was that just making the feed-forward network, the SFN module, modality specific, so separate FFN layers for the image tower, text tower, etc., that alone gave a huge performance boost, especially for images. It strongly suggests that processing the unique features of each modality through its own dedicated feed-forward layers is really crucial.
And what about the other transformer components? They looked at the attention mechanism, the query, key, value matrices, and also the layer norm layers.
Right. They found that untying the Q, K, and V matrices in the attention mechanism also gave significant gains. So having modality-specific attention helps the model focus on the most relevant bits within each data type. But interestingly, making the layer norm layers modality-specific, that had almost no impact on performance. So it really helps narrow down where the specialization matters most, largely in the feed-forward and attention parts of the transformer.
The paper also talks about modality combination and competition using these leave one out or LEO experiments. So they trained models without one of the modalities to see how the towers interact. What came out of those studies?
Yeah, these involve training moat but deliberately leaving out speech or image or text during the process. And the results showed some interesting kind of non-symmetrical effects. For instance, when they trained without speech, the LOO speech model obviously couldn't do speech tasks. But the performance gains they saw in image and text when all three were trained together also vanished. And they saw similar things when leaving out image or text.
Huh. So it's not just that each modality adds its own bit independently, there's some kind of like synergy when they're all trained together in the moat setup.
Exactly. It seems that even though the core transformer blocks have separate parameters, the joint training process itself allows the model to learn better representations overall. The fact that the full Mochive setup consistently did better than any of the Leave One Out versions really underlines the benefit of having dedicated processing for each modality, but within a shared training framework.
Okay, and finally, let's touch on those experiments where they combine MoT with a standard MoE model, MoE4X, but specifically inside the text transformer tower. Why try that hybrid approach, and what happened?
Well, the thinking there is to see if they could push the text performance even further. Remember, text didn't see quite the same huge gains from pure MoT at larger scales as images get. So by slotting a 4-expert MoE layer into the text tower of a MoE architecture, they were looking to get the best of both worlds, kind of leveraging MoE's capacity, specifically for the complexities of language.
And did that hybrid work out? Any clear advantages?
It did, actually. Figure 16 shows it led to a noticeably faster drop in the text training loss, and importantly, it did this without hurting Mote's efficiency on the image side. In many cases, this combined model either kept the image performance the same or even slightly improved it while getting consistent gains in text validation results. It really suggests that maybe selectively adding MoE layers into specific towers within the broader Mote structure could be a really promising way forward. It lets you fine-tune the capacity for each modality.
So you could imagine future models having this core moat structure with towers for different data, but maybe some towers, like the text one, get enhanced with MoE layers to really grapple with language.
Precisely, it offers a more flexible, more tailored way to build these incredibly complex systems, using the strengths of different architectures where they fit best.
That's fascinating. The paper also just briefly mentions the practical side, deploying these models, the challenges of doing inference efficiently.
Yeah, they point out that in the real world, requests don't come in neat batches of just text or just images, right? You get text, then an image upload, then maybe speech. So to use the hardware efficiently, especially GPUs, you need techniques like dynamic or continuous batching. These try to group similar operations together across different requests as they come in. That lets you use those highly optimized math kernels better. They also mention the trade-off. Do your pad shredder sequences so you can compute things simultaneously, or do you process serially for maybe lower latency on single requests? These are, real engineering choices for making these models usable.
Okay, let's try and wrap this up. In this deep dive, we've really looked at the mixture of transformers moat. And its big innovation seems to be this modality-specific parameter decoupling, using mostly separate transformer networks for different kinds of data.
That's the core idea, yes. And this separation leads to pretty clear wins in training efficiency and overall performance, especially for the test of like image generation. And what's quite striking is that this relatively simple rule-based routing, just sending data to the right tower based on modality, seems to work better, or at least more efficiently, than the complex learned routing you find in standard MOE models.
Right. And we saw these benefits hold up across different model sizes, and that moat makes multi-objective training more efficient too.
Exactly. Plus, those early experiments mixing moat and MOE inside specific towers hint at really interesting future directions for building even more capable multimodal AI.
So when you think about these mode advancements, it really helps you wonder, doesn't it, what new possibilities open up for multimodal AI with models that are more efficient, more powerful, and maybe truly understand and generate across all these different data types? What kinds of new applications, what breakthroughs could we see as AI gets better at interacting with our multisensory world? It's definitely something profound to think about. Thanks for joining me for this deep dive.
My pleasure. It was a great discussion.